Hey, we've got 5-7, contraction of the whole muscle. We're going to take a look at, we've got the idea of what's going on with the muscles on an individual level, like with the actin and the myosin. So now we need to see kind of how it occurs on a bigger level so I can get the whole muscle to contract. So muscles have the ability to either lift something as gentle as a feather or something as big and fat as a whole entire bird. So what allows you to pick up a feather with the same force as opposed to, if you tried to pick up a bird with the force of a feather, it wouldn't work. If you tried to pick up a feather with the force of picking up the bird, you'd fling it everywhere. So what is it that allows you to change how much force you put into a contraction? So we have something called tension. Tension is what they refer to as the force of a contraction. So the more tension, the greater the force. There's three things that affect the tension. One is how often the muscle fibers get stimulated by your brain. 2, the number of motor units recruited, meaning how many fibers are called into play. And then also 3, the degree of muscle stretch. So we'll go into each of those individually. All right, so let's get some vocab out of the way. The first one is muscle tension. So muscle tension is the force exerted by a contracting muscle on an object. So if we look at the picture down here, the muscle is applying a force onto the weight right here. And so therefore you can measure the tension applied by the muscle onto that object. And so you can put little receptors on there, and it goes to a little machine and it'll measure it in volts or whatever, and that'll measure the tension. The load is the opposing force exerted on the muscle by the weight. So gravity is causing this guy to pull downwards, and so your muscle is trying to pull upwards. My lights just went out again because it thinks I'm not here, so sorry if you can't see my face very well. So the load is what the weights are doing and pulling and posing against your muscle, and your muscle is trying to pull upwards against opposite the load. And there's 2 ways your muscles can do this, isometrically and isotonically. So if you know anything about exercise, isometric contraction or isometric exercises are those where a contraction doesn't move the weight. So if you pull up on something that's so ridiculously heavy it won't move. So you've got a 300-pound rock and it's got a handle. Use your imagination. You could pull, you're applying a force, but the rock's not going anywhere. So that's called isometric. But if it's a smaller rock and I pick it up, and so the force of my arm is more than the load, and I can move it, that is called an isotonic contraction. So isometric, metric doesn't move. Isotonic, it does move. Okay, so whenever my muscle contracts, I can put a little device on it and record the electrical activity that's going on in my muscle, and we refer to that as a myogram. Myomuscle gram just refers to the picture. So it's a graphic recording of the contractile activity of a single muscle. Unfortunately, we don't have cool machines like that here, or else I could show you what your muscles do when they contract. So anytime a muscle does something, moves, we call that a twitch, a muscle twitch. A muscle twitch is the response of a motor unit, one single motor unit, to a single action potential. So all we're doing is just taking a look at, here's my brain, it sent the information down to the axon terminal, and it told my muscle to do one thing. That is a twitch. So it's not multiple information being sent, it's not multiple contraction, it's just one. It's like a reflex. You touch it, it responds, you're done. So that's a muscle twitch. And it always looks like this. There's this period of just kind of flatness going on there. They call that the latent period. We'll get into each of these phases in a minute. Then where it starts to go up, and we're measuring the tension. You can also put millivolts over here because we're measuring the voltage of your muscle as well. And then as it goes up, we call that the contraction period. And then we have this nice slope down. That's called the relaxation period. So during a twitch, the fiber contracts very quickly and then relaxes, and it always shows up in these 3 distinct phases. So let's look at the phases. The first phase right here is the latent period, and this little arrow right here is showing where I applied the shock to your muscle, or my brain sent this message down to your muscle. So it's just a few milliseconds long, and it follows a stimulation. And this is where the excitation contraction coupling is occurring. So this is where the myosin is getting ready to grab onto the actin. And so that takes a few seconds. It takes a few seconds for it to go from your brain down there, affect the muscle. Then the muscle has to release the calcium in, and then the calcium has to go unlock the troponin and tropomyosin. So it takes a few milliseconds for that to occur. So that is the latent period where there's no activity. The tension increases, but there's no response on the myogram. So it's just basically the actin myosin getting ready to do their job. The next one is called the period of contraction, and that's where we actually start to see cross bridges are being formed. It's moving, if here's a myosin, and then here's my actin is now on the move. It's starting to go. And so as the actin is sliding across, then that starts to go up. Then it gets to the point where I can't move my actin anymore. It's gotten as far as it can go. That's when I hit the top of the curve here. So my actin cannot be contracted any further. Then we have the third one, the period of relaxation. That's when the calcium goes back into the SR and the muscle cannot contract. So what's happening is the actin and the myosin, the actin is going back to its original resting spot. Calcium's going back into the sarcoplasmic reticulum, and then everything's resetting back to normal. During this period, if I stimulate the cell, like an action potential goes by, since there's not enough calcium inside of the sarcoplasmic reticulum, no more calcium will come out. So during this period, I cannot have a contraction. So if my brain says, move, nothing's going to happen because I have to wait for the relaxation. But right there, if I do it again, all my calcium's back and I can do it all over again. Okay. When I look at myograms, I see different types of shapes on my myogram. And these are called graded muscle responses. So the muscles, smooth, not really smooth. Smooth not as in smooth cardiac skeletal muscle, but smooth as in smooth muscle contractions vary in their strength. And so in a twitch, what we see is just a basic standard bell curve. So you got your latent period, contract, relax, done. But our muscles don't just go like that. They're slow and graded. And so what we have to do is we have to change the amount of stimulation we give. A twitch is just your brain going twitch and you're done. But your brain doesn't do that with your muscles. It goes twitch, twitch, twitch in fractions of a second. And so what happens is you get the contraction, but instead of going down and resting, if I can stimulate it on the downfall, then I can get it to go a little bit more. Now, I said that there's no contraction during the relaxation period. No, I guess that wasn't too entirely true because, yeah, you can do a little bit. The only problem is it's not going to be as big of a contraction. So this is called a wave summation, and so it contracts, and then before it gets a chance to go back down, I stimulate again, so it goes up, and then it wants to go back down, but I stimulate it again, it goes up, and then eventually I leave it alone and it goes back down. There's another one, it's called unfused or incomplete tetanus, and that's where my stimulations come so close together that my muscle doesn't get a chance to fully relax, and so it kind of twitches. And then we have fused tetanus, which is the stimulations are just right on top of each other, so we don't see these little dips in there, and it eventually just becomes a straight line. Now, if I looked at it up close, it probably would have a very small wiggle to it, but for the most part, it looks like a smooth straight line. So anytime I lift up my muscle and hold it there, that's fused tetanus, because I'm constantly sending message to my arm, my muscle, to keep contracting, and not just because if it was a twitch, I'd be like, I'm done. So if I want it to stay there, I have to keep on sending a message to my brain and keep it in a contracted state. So how do I change all this? Well, I can change the frequency of the stimulation, causing it to stimulate more frequently. I can also change the strength of the stimulation. So if I just barely zap it, but if I just send a lot of energy, like that. So we're going to see how those two things can affect it. So one, frequency. If two identical stimuli are sent to the muscle, just one right after each other, each twitch will get successively a tad bigger than the previous. So I start it, it goes up, it wanted to go down and be a single twitch, but I stimulated again right here, so it went up, and it wants to go down, but I stimulated again, so it goes, okay, fine, it goes up. He wants to go back down and rest, but I stimulate it one more time, and then he goes up and finishes it, and then finally he can rest. So these little green arrows just show every time my brain goes do something. So we call that a wave summation. It occurs because the first twitch didn't fully relax before the muscle has fully relaxed, and so we get a culmination of twitches upon each other. If a stimulation occurs before repolarization, then no summation occurs. So I have to wait for my cell membrane to be repolarized in order for this to occur. Okay, there's something called TREP, although if you watch the little slideshow on the interactive physiology, she calls it TREPA, which sounds funny. But it's TREP. It's called the staircase effect, and that's just what we call this pattern of it getting, higher and higher like that. So it's a staircase pattern caused by the increasing strength of the muscle contraction. So what ends up looking like is this. Okay, then we have unfused or incomplete tetanus, and that's what happens when we start increasing the frequency so much that they almost kind of fuse together. But it's called unfused because we do have little dips in there. So it looks like my muscle wants to go back down, but I grab it before, and so it goes up. So in the previous one, there are bigger dips between them, whereas this one, the dips are much, much smaller. So we call that unfused or incomplete tetanus. That's when contractions fuse into a quivering contraction caused by decrease in time between stimuli and build of calcium concentration in the cytoplasm. And then we have fused tetanus, which is where that would have been a twitch right there, but if I can just keep on stimulating it over, it just eventually maxes out and fuses into a nice, smooth, sustained contraction caused by no relaxation. So there's no dips in between. Oops. Oh, no. Where am I going? Sorry. Okay. So the next one is fatigue. Fatigue is what happens when the muscle's no longer able to keep up its tension. So it's going up and it's fused, but then your muscle is just like, I'm trying, I can't do it, and then it gives up. So you're lifting weights, and then after a while, you're like, nope, ain't happening, I'm done. So that's muscle fatigue, and what happens here is that there's a buildup of acidic compounds like lactic acid that affect the protein function, proteins like actin and myosin, lack of ATP, and so if I don't have the energy, I can't keep it going, and ion imbalances with the sarcolemma and so on. And so what ends up happening is once it starts smoothly going back down, we call that muscle fatigue. So you have to wait for it to kind of smooth out flat again, give it a time to rest, and now when I stimulate it, it should go back up. Because if I try to stimulate it now, nothing's going to happen. Okay, next one, number of motor units recruited can affect the contraction. So we have something called a multiple motor summation. Now remember we said that one axon comes down and affects a particular cell, but that axon can be split into several different fibers like this. So multiple motor summation means to add together, is when many motor units control muscle contractions more precisely. And so if I just want something small to go, I'm only going to tell a couple of muscle cells to do its thing. But if I need to pick up something really, really heavy, my brain needs to tell as many muscle cells as possible to get going and start contracting. So we call that recruitment. Recruitment is my brain telling other muscle cells, hey, wake up, it's time to get to work. So my brain sends a higher voltage to the muscles, and that wakes up more cells, telling them time to get to work. There's this thing called the threshold, threshold stimulus, which is the stimulus at which the first observable contraction occurs. So if I'm zapping my muscle cells with my brain, and in small volts, then my muscle cells are going to be like, yeah. So I increase the voltage, no. Increase the voltage a little more, okay, and then the cells start moving. So a threshold stimulus is the stimulus, or the voltage almost, that is minimally required in order to get a contraction to go. Then we have maximal stimulus, which means that it's the strongest voltage at which I can get my muscles to contract. So there's a point where, like, if I zap it with, say, 20 millivolts, it's going to contract. If I do 30 millivolts, it's going to go higher. But then there's a point where if I do 100 millivolts, it's still only going to go as high as my highest one's going to allow. So that's a maximal stimulus. Okay, almost done. The strength of a muscle contraction is determined by the frequency of the stimulation and the number and size of the motor units recruited. So those are the first two items. And the number of motor units recruited is determined by the number of motor neurons stimulated. So if I only stimulate one motor neuron, I'm only going to affect this many muscles. But if I stimulate many motor neurons, and with all their little branches, well then I'm going to get way more muscles involved. All right, last little thing that affects how well your muscles work is something called stretch. They also refer to as the length-tension relationship. The strength of a muscle contraction can be affected by changing the starting length of a muscle. So if here is my myosin and here's my actin, if I start with a little bit of overlap there, my muscles should work fairly well. But if I start with, here's my myosin, here's my 2-actin, if they're already close together, my muscle obviously doesn't have much room to grow, and so we're not going to get a whole lot of contraction. If my myosin is here and my actin doesn't even overlap with the myosin, then there's no cross bridge formation. There's nothing for him to grab onto. So if you overstretch your muscles, then your muscles won't work as well. So in an unstretched muscle, the overlapping thin filaments will interfere with each other, causing problems with the cross bridge formation. If I overstretch my muscles, there's hardly any overlap, and so there's nothing for the myosin to grab onto. But if I moderately stretch my muscles, that will provide maximum tension, and because there's an optimum overlap between the thin and thick filaments, allowing all cross bridges to be formed. And so that's why it's always good to stretch a little bit before, because if you start out unstretched, there's too much overlapping and they get all tangled up. If you overstretch, there's nothing for them to grab onto. So you want to stretch a little bit, because then that'll allow for optimum or the most cross bridges to occur. Okay, that's it. I'm sorry. It's almost 17 minutes. I'll shut up now. Okay, bye.